Let us now define the electrical term known as resistivity. And here is the symbol. Let that sink in for a minute. No, it's not linear momentum, nor is it volume charge density. Listen now, I'm just the messenger. I did not define this. Don't ask me why they're using rho over and over again. I guess because it's easy to write, and there just isn't a voluminous enough Greek alphabet to do justice to all the parameters we want to specify. So there you go. Deal with it. Well, what is it? Resistivity, rho, equals electric field over current density. That's right, electric field over current density. Now I know you're thinking, what the heck? Let's see, electric field, force per charge over current per area. Yeah, force per charge over current per area. Oh, that's a nice intuition. I've got a wonderful intuition as to what that means. Okay, well maybe you've already got a more simplified understanding here. Let me give it to you if not. So you think of it as, for a given current density, how do you get, that's the flow of charges across a cross-sectional area. And so you need a certain amount of push to get those charges to move. That push is from the electric field. So if you need a little tiny electric field for a given current density, you have a small resistivity. Aha! Low resistivity to the flow of current. If you need a high electric field for a given current density, you have a high resistivity. Now you have the intuition. Let's move on. Volts per meter over amps per meter squared. Volts over amps times meters. Do you remember from first year of physics what a volt over amp is? Ohm's law. Volts over amps is ohms. So this is ohm meters. So there is the unit for resistivity. It's a characteristic property of materials. Conductors. They range from about a micro ohm per meter to about 1/100th of that. So very, very small values of resistivity. Insulators, on the other hand, greater than 10 to the 8th ohm meters, not -8. So it's the other end of the spectrum. And semiconductors span a wide range somewhere in the middle, -5 to 10 to the 3rd or so. Particular value depends a lot on the impurities added to the semiconductor, which is, the base is usually silicon. They add impurities to get the substance doing what it needs to do to build your microprocessors and transistor amplifiers and whatnot. Now, an ohmic material has the property that the resistivity is constant. In other words, it's not temperature dependent. However, most materials don't follow that rule. So for instance, for metals, we have a relationship kind of like this. As you heat the metal, the resistivity goes up. How about semiconductors? Well, they have a very high and inverse relationship with temperature. So the resistivity goes down as temperature goes up. A good way to think about that is, basically, in a semiconductor material, you heat it up and you have a lot of jostling. You're reducing the energy barrier of free charges to move across the semiconductor junctions that enable the material to function in an electronic circuit. So it radically alters the way in which the semiconductor material functions. And then we have superconductors. Oh, that's exciting. Superconductors have this unique characteristic where there's no resistivity at very low temperatures, and all of a sudden there's a unit step change and it suddenly has resistance, and then it acts basically non-ohmic like a metal typically, and goes up with temperature. Now for metals, the resistivity is a function of temperature, something like this. You don't have to know that formula. Just realize that there's some reference value at a reference temperature. Okay, so T0 is some reference temperature, and this resistivity tends to go up as the temperature goes up. So that's just by way of background. And now let's move on to the idea of resistance. So, resistance. We start with Rho equals E over J. Now, those are hard quantities to measure. You can't directly measure electric field and current density with some kind of multimeter is what I'm thinking of. But it's easy to measure voltage and current. Yes, it is. Well, let's take a look at the quantities in a current-carrying conductor. So here's our conductor, and it's going to carry current. It's got length L, and it's got cross-sectional area A. It's going to have an electric field that's pointing in this direction, which means, I hope you realize, that the voltage increases in this direction. As we go in this direction against the E field, we're going from lower to higher potential. Now, something may be bothering you right now, so let me just clear the air here. I don't think I've said this yet. I've harped ad nauseum almost, or at least at length, on how an electric field can't exist in a conductor. Well, that's true if the conductor is perfect. But these are imperfect conductors, so you can have a small electric field existing. In fact, if you think about current flowing, so we're not talking electrostatics now. We have the flow of current, which requires forces to be on those charges. Forces are produced by electric fields, so to keep the current flowing, you need an ongoing electric field that's ushering those charges along. So that is a new kind of mini paradigm that we're working under with current electricity. Then we have this current I, positive current, which results in a current density, vector current density, like this in the direction of positive current. Now inside the conductor, if the resistivity is uniform, so is the electric field. And from this we can discuss how we define the electric field, which is, remember, volts is E field times length, integral of E dot dl. So E is V over L in this case. And J is just simply I over A. Oh, so resistivity is E over J, so it's V over L over I over A. There it is. Which gives us VA over IL. So VA over I then is rho L over A. Well, this is kind of special. All these parameters here, rho, L, and A, are properties of the conductor, not quantities flowing or that the conductor is subjected to. And that rho L over A combination is called resistance, short R, and the symbol for that is omega. So that's how we define resistance. Here it is, V over I equals R is rho L over A, and that really is Ohm's law. You might recognize it. If not, there it is, and we're going to be using it. Ohm's law relates volts, current, and resistance. And it also relates it to resistivity, the characteristic property of a material, times its length divided by its surface area. So resistance is proportional to L, inversely proportional to A. So 1 ohm is a volt amp. It's equal to volts over current. And resistance is a function of temperature just because of the non-ohmic nature of materials. So there it is. And that's a quick and brief and hopefully fairly concise overview of Ohm's law, resistance, and resistivity. Let's do a quick, easy example using some of these ideas. We're going to find the electric field in a copper wire. And the diameter is given, cross-sectional area, and the current. So here's the wire. We're going to find the electric field in this thing. All right. So cross-sectional area, current, and E field. What is it? What's that E field? Again, we need the E field to get the current to flow. Now from engineering book of some sort, tables, the resistivity of copper, very low. Copper is a very good conductor. All right. So E field, rho J. Rho J, current per area, equals 0.035 volts per meter. So there's the E field, small E field. What's the voltage and resistance of 50 meters of this wire? Well, the voltage, V, is equal to E field times length. E field was given, or we computed, length given, gives us 1.75 volts. So 50 meters, 1.75 volts. Not a whole lot. Realize, of course, that as current goes up, the E field will go up because the current density goes up. So all this changes when the current increases. Now, the resistance is simply V over I. V over I, 1 ohm. So 50 meters, 1 ohm. Not very much. A very good conductor, which is also rho L over A. Well, because this is AP Physics, we can't just only do simple problems. We got to do a little more challenging one as well here. So we have a hollow cylinder, length L, inner and outer radii A and B, uniform volume charge density rho. All right, now, did I say volume charge density? I did, and you caught me. It's actually resistivity. But I wasn't just kidding. It slipped my tongue. Okay, moving on. We set up a potential difference between the inner and outer surfaces. So we put a potential difference from the inside to the outside. So current flows radially through the material, and we need to figure out the resistance of that. Now I know even after I just said that, you want to get the resistance from one end to the other, because oh, that'd be so nice and simple. It's just, you know, directly proportional to the resistivity and the length. But not so simple, because we're going to have it flow from inside to the outside. You get what I'm talking about? So here's a cross-sectional area, and we have our inner and outer radii. And so we got to get charge to flow from here to the outside, from inside to outside. So there's a current density, and I'm showing it in 4 places. It's uniform. Everything is uniform here. But this non-trivializes it a little bit, as we'll soon see. So we're going to have this charge, the current flow from in to out. We're going to make a little tube. This red ring is really a red tube going through there. Material, thickness dr. Why am I doing that? Well, the resistance is rho L over A, so we know that. The current has to all pass through this red differential tube, and it's going to have to do that with an infinite number of other ones as well. All right, so, well, before I get further into that, can't we just say rho? The length is just B minus A, this length across here from inside to out over A. And of course the answer is no. And why? Because that cross-sectional area that it's going through, not this cross-sectional view, as I'm saying here, not this area, but the area of the tube from the inside to the outside, or right? As we think of the tube of this radius, that surface area along this whole thing, okay, and then increasingly large radii, and that's the whole point. The area is not constant, but it's increasing as we go toward B because the radii is getting bigger. Are you following this still? Good. So what we got to do is get the differential resistance. That'll be the resistance of this little differential tube of material with resistivity rho. And it's rho L over A. Rho L, differential R, over A, 2 pi r, this might help you, 2 pi r, the circumference times the length. That's the area where the current's flowing through. So the resistance is just the integral of all that, and the rho, the 2 pi, the L are constants, so we integrate from A to B, 1 over r dr, and we get a wonderful, actually simple result that we can now just write down. There it is, folks. Rho over 2 pi L, natural log of B over A. I'm sure that was very satisfying, and you feel now like you can handle basic resistance and resistivity problems.